Welcome to a lesson with Dr. Powell. Remember that shorthand notation we're using for operations and outputs of functions? Well, what we were doing with those outputs of functions to make a new machine in the last example looks something like this. And we input 3, but we could have input anything. So just let that be an X. So what we were doing here, that we made a new function out of the old functions. And it was defined precisely by taking the outputs of this one, the outputs of that one, the outputs of this one. Now, whenever we make new functions in such a way, we need to be careful about what is actually acceptable to plug in. What's acceptable to plug in here, so kind of like the domain of this guy, of this new creation that we made, has to follow, well, first of all, it has to be able to be plugged into F, it has to be able to be plugged into G, and it has to be able to be plugged into H. And it has to make sure that any new restrictions that I put in here, like a division or whatever, have to work out. Let's look at an example. Let's suppose, for instance, that we have f of x is equal to x squared minus 9. And maybe we have g of x is equal to x plus 3. Okay, now let's look at the function, the f over g function of x, which means you plug x into f, you plug x into g, and then after you plug them into this and this, then you perform a division. Notice this function doesn't say anything about simplifying here. Actually, when you simplify an algebraic expression, you actually change it to a different function because you might change its domain sometimes. And this is an example. Because if we write this in longhand, this means you put x into f, which means you simply have f of x and the result over g of x. And you plug in what this is, x squared minus 9 over x plus 3. This is the function, halt and stop. Don't do anything else. This right here is the function the expression that determines what the domain is. Don't try to simplify or anything. It's tempting to think, if you knew how to factor this, x plus 3 and x minus 3, it's tempting to say, hey, look, those cancel. This is just equal to x minus 3. Well, as algebraic expressions, this is, but as functions, it's not. The reason why it's not is because what is the domain of this expression? It's everything. You can plug anything into here. But can you plug everything into here? The answer is no. You don't want to divide by 0. X can't be equal to negative 3. If you change the domain, you've actually changed the function, because a function is inherently a rule or a formula, but also a domain. And you have to specify the domain. And that really makes a function what it is. So it's funny because when you do algebraic cancellations, you actually, even though you don't change, you have an algebraic equivalence, it's not a function equivalence. You actually change your function. So this would be wrong. This function is not this one. This one is this one, but not this one. So be extra careful. In fact, we can see exactly what the domain of this function is just from this form before we do any cancellation work. X is not equal to negative 3. However, if we really like this formula better, we can still use it. But remember the trick that we have with the comma? We better use it now and impose a restriction. And the restriction we impose is x is not equal to negative 3. All of a sudden, it works. This now is equal to this as a function. Notice the comma means we only put that in when we're talking about expressions as representing a y equals with a function. So as a function, this now is equal to that. So if you want to reduce to something simpler, go ahead, but please put a comma down and put down what the domain really is. In this case, it's x is not equal to negative 3. Thanks for watching.